All right, so today we're going to be talking about inverse functions, and of course, with inverse functions, we're also going to squeeze in logarithms, mainly because Section 5 had to do with exponential functions. And as if you remember from analysis, and I'll probably clarify today as well, logarithmic functions are definitely, in fact, the inverses of exponential functions. So let's start off simply by defining when a function is one-to-one. And we'll talk about the importance of why we want functions to be one-to-one. So we could say that a function f is called a one-to-one function if it never takes on the same value twice. So in other words, that is, to put this mathematically, we're saying f of x sub 1 will never equal to f of x sub 2 whenever x sub 1 doesn't equal to x sub 2. So in other words, what we're saying is, if you have a one-to-one function, if I plug in two different inputs into that function, their y values will never ever equal to each other. So for instance, if I tell you that I'm thinking of a one-to-one function, and you don't have to put this in your notes, you could just pay attention to what I'm saying, but if I tell you, hey, look, f is a one-to-one function, and if f is one-to-one, and this, by the way, this is a short way of writing a function as one-to-one, so maybe I should put it up here. So when you see 1-1, we just mean one-to-one. So if I tell you, for instance, f is one-to-one, and I tell you that f of x sub 1 equals to f of x sub 2, then what's the conclusion you're going to make? And the conclusion you should make is you should say that, look, since f is one-to-one, and I know that for one-to-one functions, only one x value could take me to a singular y value, then that means f of x sub 1, if f of x sub 1 equals to f of x sub 2, then that means that x sub 1 and x sub 2 have to be the same x value. Okay, and so that's the case. So to kind of clarify it even more, take into consideration f of x equals to x cubed. That's a one-to-one function, right? Because notice what happens is, if I plug in 1 for x, I'll get 1. But that's the only way I could get an output of 1. So if I tell you that for this function, I'm thinking of, let's say if I tell you that, look, f of x1 equals to f of x2, which is 8, for instance, for this, you'd say, wait a minute, this is impossible. Or the only way f of x1 will equal to f of x2, which is 8, is if both x1 and x2 are 2. And that's kind of like what's going on here. All right, so for one-to-one functions, what we know is each x value takes me to a unique y value. So let's look at our first example. And this is actually going to have a quick solution. And the question is f of x equal to 3x to the 5th one-to-one? And the solution to this is the following. And this is kind of like a generic way of doing this. Notice how what we could say is if x sub 1 doesn't equal to x sub 2, so if I pick any two random x values, and what gives it away is this odd exponent. If x sub 1 doesn't equal to x sub 2, then we know that the outputs are definitely not going to equal. Then f of x sub 1 will not equal to f of x sub 2. Okay, and that's going to be a fact. No matter if I plug in two different x values, my y values at those different x values are going to be different, which by definition, that's what a one-to-one function is. So we could say, therefore, this is one-to-one. Okay, and that's kind of what we're doing here. Now, we also know that we can visually check to see if a function is one-to-one, and that's through the horizontal line test. And so I'm sure you've had a lot of experience with this. So I'm just going to give you the definition or how we describe the horizontal line test, and then I might draw a quick picture and we could move on. So we could say that a function is 1-to-1 if and only if, I don't know if I've mentioned this before, if you see an if with two f's, this is how we write if and only if. It's a short way of writing if and only if. So if and only if no horizontal line intersects its graph more than once. So basically what we're saying is, visually speaking, now why does this satisfy, or why does this help us determine if a function is one-to-one or not? Because think of it this way. We all know that a parabola is clearly not one-to-one. Now, why is it not one-to-one? Think about it. If I draw a horizontal line, notice how this horizontal line intersects this graph in more than one place. And so what are we showing? I just showed two different x values took me to took me to the same y value, and that contradicts what a one-to-one function is. Whereas if I have like a cubic function, notice how each horizontal line I draw has only one y value that satisfies that x value. So notice how the only x value that will produce this y value is that one and only that one, and therefore this is one-to-one. Okay, so moving on. Now, what we're going to define now is an inverse function. And so now hopefully we'll clear up why we care for something to be one-to-one. So we're going to say let f be a one-to-one function with domain A and range B. So the only thing that so far we've defined is I'm telling you that f is a one-to-one function, its domain is A, and its range is B. Okay, so now we could say then its inverse function, f inverse, has domain B and range A, and is defined by f inverse of y equals to x, or better yet, equivalently, we could say f of x equals to y. Okay, for any y in B. Okay, so let me point out to you, first of all, why it's important for f to be one-to-one. Because if my function f is not a one-to-one function, then it has no inverse. Okay, reason being, notice how we're calling this an inverse function. What's the problem if a function is not one-to-one? So, for example, if we come back to the parabola, and I draw this, and I say, look, this, for it to be an inverse, or by definition, and let's ignore the fact that it's not one-to-one, and we'll see that how we're going to run into problems here. So here's what we're claiming. This is f of x equals to x squared. So by definition, what is it that we know? The domain of f becomes the range of f inverse. Okay, now here's the problem. If this function, we talk about its inverse we're going to claim looks like this. Okay, because what happens is that the x values of this guy become the y values of this guy. So what do I notice? This guy at x equals 2 and x equals -2 has a y value of 4. So what does that mean? This guy, when it has an x value of 4, it has a y value of 2 and -2. Now, hopefully you guys see the problem we have here. This is not a function. It fails the vertical line test. And so what we notice is, for me to have an inverse function, the original function has to be 1-to-1, because if it's not, then its inverse is not a function. So we can't really call it an inverse function. Okay, so that's the big idea here. That's why we want it to be 1-to-1. Okay, now moving on, let's make some comments here. What we said in this definition is that we're claiming that the domain of f inverse equals to the range of f. And also, the range of f inverse equals to the domain of f. Okay, and that's kind of like what all of this definition is saying. Now, usually I draw this visual, and I'm going to draw a couple of blobs, and so don't pay attention to the blobs. It's kind of like saying, look, pretend that this is the set A in our definition. Remember how we said f has a domain of A, and this is the set B. So basically what we're saying is this, each x value in this blob is the domain value of f. And so what I know is that when I plug in x into f is going to put us out, or is going to give an output of y. So that's what f is going to do. And since it's 1-to-1, what I know is that only this x will take me to that y. It's impossible for me to find another x that will take me to the same y. And so what does the inverse do? The inverse takes me back from y to x. So if you look at this, when I draw this out, that's f inverse. And so notice how we were saying earlier on, if I move this back up, notice how I set f inverse of y equals to x. Well, if I come back to this picture, then that will make a lot more sense, because look, here's f inverse of y. I plug this in and it becomes x. So if you look at this, the domain of x becomes the range of f inverse, because this is my input and f inverse puts me there. Okay, and then also the range of f becomes the domain of f inverse. So this picture, although it's simple looking, kind of does a good job of summarizing what's going on with this definition. Okay, now one other thing I want to point out is, and this picture is actually pretty helpful. See, in previous classes, you may have been told that, look, f inverse of f of x is just x, because f inverse and f, they cancel each other out. And I kind of don't like that terminology. I actually like to think of this as a mapping. So why does f inverse of f of x equal to x? So it's not really that they cancel each other out. It's kind of like they undo one another. Because look at what happens here. If I treat this as a composite function, I'm talking about f of x, right? So if I come back to this picture, to get f of x, what does that mean? I need to plug in x into this function. So if I plug in x into f of x is going to take me to y. So what happens here is, based on this picture, if you look at this, we notice that f of x becomes y. So I could change this to what? F inverse of y. All I really did is I just said, okay, look, f of x takes me to y. And look at what happens now. F inverse of y, which if I come back to this picture, f inverse of y takes me back to x. So it's kind of like wherever f of x takes me, f inverse takes me back to x, which is how we get to x. So that's why we could say that f inverse of f of x equals to x. It's just kind of like one does one thing, the other undoes it. And of course, we can go the other way. We could say f of f inverse of x, that's equal to x as well. It's because whatever f inverse does, f does the opposite, or undoes it, and takes us back to where we were. Okay, so that's kind of like the explanation. Usually this picture does a good job of describing it. Okay, so now let's go into finding the inverse of a function. Okay, so keep in mind that when we're finding the inverse of a function, in parentheses, I'm going to put if possible, because there may be functions out there where when you try to find its inverse, and in fact, there may be one-to-one functions out there, when you try to find their inverse, it becomes really, really difficult, and it's kind of like good luck finding it. So in fact, for homework, I think you have one, and I'm sure you're going to have questions on that, and we'll talk about how we would approach that, because finding the inverse of a function isn't always the best way to approach it. But if I give you a function and I ask you specifically to find the inverse, I'm sure you already know how to do that. So the first step in analysis, you guys said, we're going to interchange x and y. And then once you do that, second step would be you solve for y. And when you solve for y, that function that you get, that is your inverse. And there you have it. You have your inverse taken care of. Now, one comment I want to make here is that how do we graph the inverse of a function graphically or visually? And that, if you remember, the graph of f inverse is obtained by reflecting the graph of f about the line y equals to x. Okay, and so that's kind of like how we can produce the inverse visually. Okay, now with that said, let's now turn our attention to logarithmic functions. Okay, and logarithmic functions are in fact inverses of exponentials, and I'll show you that again just to kind of verify it. But if you remember, we defined a logarithmic function as follows. The log of any base a of x, if that equals to y, that says the same thing as a to the power of y equals to x. And so if you remember, we would always say a to the power of y equals to x, and that's what it is. So what makes logs complicated is when people try to think of it this way. I personally like to always grab a logarithmic function and write it in exponential form, okay? And so one other comment I want to make is where a has to be a positive number and a can't equal to 1. Okay, and so those are kind of like the standards here. We get into problems if a is a negative number or 0. We start noticing none of this makes sense. Okay, so the base has to be a positive number and it can't equal to 1. Okay, so one thing that I want to point out here is hopefully you guys already see why logarithmic function is the inverse of an exponential, because by definition we define an exponential function as y equals a to the x. And if I asked you to find the inverse of this, just like the steps I gave you before this, you would first graph, so this is exponential. That's my exponential function. So if I want to find the inverse, I would swap x and y. And if I swap x and y, I get x equals to a to the power of y. And then we say, okay, once you do that, now I need to solve for y. But if you look at this, doesn't that look like that? And so what does that mean? If x equals a to the y, that's the same thing as y equals to log base a of x, which in fact, that's the inverse of the exponential. Okay, so logarithmic functions are literally just the inverse of exponentials. Okay, so that's the first definition that I want to give you. Now the second definition is more kind of like a property of logarithm, and we have log base a of a to the power of x. And if you remember this from analysis, we said log base a of a, since these two are the same, this ends up just being x. And then that's for all x in the real number. If you haven't seen this upside down a, I think this is the first time I'm showing you, that just means for every. Okay, so basically that's a quick way of saying for all x. And this weird looking e, I think that I've shown you, that just means it's in. So for any x that's in the real numbers. So for example, 2 or 5 or whatever it may be. Okay. Now we also had another property where we said if you have a to the power of log base a of x, that also equals to x, because if you have a to the power of the log of the same base, these kind of, I don't want to say cancel each other out, and I think you're going to prove this for homework. Once again, these kind of undo one another. It's kind of like the inverse of one another. You end up just getting x out of this. And then this is for all x greater than 0. Now, why is it for all x greater than 0? Because logarithm has a domain that starts from 0 and goes to infinity. So we can't have 0 or negatives in here. So if this x is a negative number, or if it's 0, then it'll be undefined anyway. Okay, so in fact, let's make a comment about that here just so we can make more sense of it. The logarithmic function has domain 0 to infinity. And so that's why x has to be greater than 0. Okay, so moving on to some of the laws of the logarithms that we've seen in analysis. And so I'm going to go through these fairly quickly, but I think it's important that you write them down anyway so you have them. So laws of a logarithm. So here are the laws that we have. If x and y are positive numbers, then we have these properties or laws of logarithm, which I'm sure you're pretty familiar with them. So the first one is log base a of x times y. If you remember, we can break this up. And if you remember the multiplication of these, we could break up as addition. So this breaks up to log of base a of x plus log of base a of y. The second property we had was log base a of x divided by y. That becomes, and if you remember, division was broken up by subtraction. So it would be log base a of x minus log base a of y. And then, of course, the third law that we're going to use is log base a of x to the power of r. If you remember, there's something we could do to this power, and that power we could bring out front, which becomes r times log base a of x, which then r is any real number. Okay. Now, one comment I want to make about this property. I had a student a few years ago approach me and say, well, Mr. Gregorian, you're telling me that this property is true, but you're also telling me that logs can't have negative values plugged into their domain. But wouldn't this work? What if I had something like this? So you don't have to put this in your notes, just kind of look at what I'm doing. What if I have something like this? 2 of log base, I don't know, let's call it 10, let's just leave it as 10, of negative 2. And see, he basically told me, you're telling me that this is undefined, and which that is correct, this is undefined. But then the point he was making is, can't I use this property and move this 2 up there and say this is log base 10 of negative 2 squared, which then negative 2 squared becomes log base 10 of 4, and shouldn't that all of a sudden work? Which means, how come this is true when I just came up with something that is weird, because you're telling me it can't be negative, but now all of a sudden it's positive and it works? And that's actually a really good question. The only mistake that the student was making was this was not defined to begin with. And if I start off with a logarithmic expression that's not defined, then I'm not allowed to use this property. So since this was negative to begin with, this property 3 could not be applied to this. So this is, I'm making some illegal moves here. So I'm not allowed to do that. Okay, so that's where the mistake comes in. So to be able to move this 2 as a power, I need to make sure that this logarithm is defined to begin with. Okay, so I hope that kind of makes things clear as to why this property, when we can use it and when we can't. Okay, now before we move on to our next example, I also want to talk about the natural logarithm. And you'll notice that I'm kind of like a sucker for the number e. I love the number e. So whatever I do is I only work, whenever I work with logs, more often than not, I work with the natural log. Okay, so the natural log doesn't really change anything. It still follows the same rules of logarithms. It's just instead of writing, so let me just kind of define it, but instead of writing it as log base e of x, this gets shortened to ln of x. So it might look different, but it's just like an ordinary logarithm. The only difference is its base is that number e. So the second thing we could say is, for example, ln of x is equal to y. That's the same thing as saying e to the power of y equals to x, okay? Um, or another way of kind of thinking of logarithms is if I have ln of e to the power of x. Now notice how this is base e of e to the power of x. This just becomes x for all x in R. So notice how this is the same definition as I gave when we talked about basic logarithms. We're just being specific to natural log right now. And then the fourth step is, what if I have e to the power of ln of x? Remember, we had a to the power of log base a, so this is the same thing, e to the power of the same base. That'll also be x, and of course, remember, x has to be greater than 0 because of the domain of ln. And then, of course, this one we should all know, ln of e is just 1, okay? And so, like I said, these properties are the same as the ones we talked about in this page right here. They're all the same thing, except instead of having a base a, now we have a base of e, which, if you remember, e is that number 2.71, so on. Okay, so let's look at our second example. So for example 2, we're going to say solve e to the power of 5 minus 3x equals to 10. Okay, now here's the problem. When I'm solving for this, one way we could solve for this is to try to get the left side and the right side to have the same base, which you could see that this is impossible. So the second way I want to solve for this is I somehow want to ground this. I want to bring this down so I could isolate x and get it by itself. So the trick is you take the log of any base of both sides. And since I told you, since I'm pretty much in love with the number e, I'm going to natural log both sides. So I'm going to ln here and ln here. So if I ln both sides, what's nice about this? Now that I've ln both sides, that allows me to bring this 5 minus 3x down to the front. So if I move that down to the front, I get 5 minus 3x times the natural log of e equals to ln of 10. And what's also even better is, what's ln of e? ln of e is that's just 1. So what I have is 5 minus 3x equals to ln of 10, and now I could solve for x. So if I subtract 5 from both sides and divide by negative 3, I get x equals to 5/3 minus ln of 10 over 3. Okay, or you could just say 1/3 times 5 minus ln of 10. Okay, so moving on to some other, one last property of logarithms, which is the change of base formula. And the change of base formula basically says, look, we can change the base of any logarithmic function to anything we want, okay? And better yet, if I could change it to anything, I'm sure you could guess by now, I want to change it to natural log. For me, it just makes it easier to deal with. So we could say for any positive number a, and just make sure that a doesn't equal to 1, we have log base a of x is equal to ln of x over ln of a. So basically, I grabbed this and I changed the base from a to e, which means that's how I got it from natural log. So you'll see this more often than not. But if you remember in analysis, and let's make a note of that here just to refresh your memory, we said in analysis that we can basically we can change the base to anything of our liking, so to anything, which means, for example, we can take log base a of x, and we can say that equals to log base b of x all over log base b of a. And so b is basically the base of my choice. So what happens is, whatever this is, the top, or think of it as this is the bottom, this is the top. So whatever's on top, that will end up in your numerator. Whatever's your original base, that'll end up in the denominator. So that's kind of what's happening. This x goes up there, this a goes down there, and then we change the base to whatever we like. Okay? Now, with that said, we're going to move on to the last topic of today's notes, which has to do with inverse trig functions. Okay? And so let's talk about inverse trig functions, because here's the problem. If you remember, so let's actually write this down, is that recall from analysis that inverse trig functions had restrictions, or they have restrictions. And why do we want inverse trig functions to have restrictions? Well, let me just give you a quick visual of it. Let's just take the graph of sine. If I draw the graph of sine, that's what I get, okay? Now, what's the problem with this? Does this graph have an inverse? And the answer to it is obviously not, because this fails the horizontal line test miserably. I mean, it crosses it infinitely many times. So what's the purpose of these restrictions? See, what we notice is, and these restrictions, like I said, it's kind of like become common practice. I guess mathematicians have discussed that, these are probably the best restrictions to use, but it doesn't really matter. But here's what we notice. The graph of sine covers y values from -1 to 1, and it just keeps repeating over and over and over. So what we said is, look, what if I create restrictions where my sine graph starts from -1 and goes all the way up to 1, and we stop it at that. See, in fact, let me show you that. So do you guys see how this graph, this portion of the sine graph, covers all the y values that sine will ever take on, right? Because it goes from -1 to 1. And so what you notice is by me setting these restrictions and cutting off this sine graph, what have I just done? I made sine into a one-to-one function. So the reason why we have these restrictions is because we're forcing sine to be one-to-one so that it has an inverse function, okay? So if you're wondering where those restrictions are coming from, it's strictly to make it one-to-one so that we can work with inverse functions. So with that said, let's talk about the inverse trig functions. So here's what we have. We know that sine inverse of x equals to y. That means the same thing as sine of y equals to x. However, and y has restrictions from pi over 2 to negative pi over 2. So the restrictions for sine inverse is from negative pi over 2 to pi over 2. Okay? And then for cosine inverse of x equals to y, that means the same thing as cosine of y equals to x. And the restrictions for cosine is from 0 to pi. Okay? So those are the restrictions to keep these one-to-one. And then we have tangent inverse of x equals to y. That means the same thing as tangent of y equals to x. And the restrictions of tangent are almost the same thing as the restrictions of sine, except it's from negative pi over 2 to pi over 2, not including negative pi over 2 and pi over 2. If you remember, tangent has vertical asymptotes there, so that's why it can't equal, because it's not defined there. Okay, and then of course we have the other trig functions, which are the cosecant, secant, and cotangent. So we could say cosecant inverse of x equals to y. That's the same thing as cosecant of y equals to x. And we can say y is less than or equal to pi over 2, greater than 0, or y is less than or equal to 3 pi over 2 and greater than pi. Okay, so those are the restrictions for cosecant. And then we have secant inverse of x equals to y, which that means secant of y equals to x. And the restrictions here are y is less than pi over 2 greater than or equal to 0, or y is greater than or equal to pi less than 3 pi over 2. Okay, now remember, these restrictions that we have, they're set in a way where it takes on every value of secant. So, and we're making it one-to-one. And then, of course, we have cotangent inverse of x equals to y. That means cotangent of y equals to x, and y is less than pi greater than 0. And those are restrictions. So anytime you're going to use your trig function inverses, you need to make sure that you take into consideration the restrictions. Okay, so keep that in mind, because that's very, very important. And we'll do an example in a minute where I'll take the restrictions into consideration. Okay, so the last set of properties I want to talk about are as follows. So we have sine inverse of sine of x. If you remember, this is the inverse of the original, which what does this do? Whatever sine does, sine inverse undoes it, which gives us x. Except the question is, what kind of a value is x going to take on? Now look, since the inverse is the last operation I perform, it's going to have the same restrictions as sine inverse, which sine inverse's restrictions up here are from where? Negative pi over 2 to pi over 2. So what we need to make sure we state is that for x is between negative pi over 2 and pi over 2. Okay, so if x isn't within these restrictions, we need to adjust it so that it is. Okay, and then we also have sine of sine inverse of x equals to x. And what do you notice here? Since sine inverse is performed first, then sine is, so the output of sine we know is always going to be between negative 1 and 1. So we could say for x is less than or equal to 1, greater than or equal to negative 1. So if x isn't between negative 1 and 1, then this is going to be undefined, because it's impossible for sine to have an output greater than 1 or less than negative 1. Okay, so for these guys, if x is not in the restriction, we can adjust it. Because remember, in analysis, when we talked about trig, we talked about coterminal angles, which means they land in the same place, so I could adjust it. But if this one, if it's out of bounds, there's nothing I could do. There are no adjustments I could make. Okay, and then of course we can do the same thing for cosine. We could say, look, cosine inverse of cosine of x, this equals to x. Now, if you remember, cosine inverse is performed last, so the restrictions for cosine inverse are from 0 to pi. And then same thing, cosine of cosine inverse of x, that's x. And since cosine is performed last, we know the output of cosine is always between negative 1 and 1. So once again, if this is out of bounds, we can adjust to fit those restrictions. If this is out of bounds, there's nothing we could do. It's undefined. Okay? So to finish off the section, we are going to do an example, which you definitely saw this in analysis, probably one of the harder topics you guys talked about in analysis. So our goal is to simplify cosine of tangent inverse of x. So what I want to do is I want to simplify this. And what you notice is, since this is in terms of x, I expect to simplify this, and I expect this to be in terms of x. Okay, so if you remember, you probably learned this in different approaches, but the approach that I take to solve for this, I use substitution. So what I'm going to do is, since this is a composite function, I'm going to start my work inside and then work my way out. So here's what I'm going to do. I'm going to say, and I'm going to be jumping back and forth quite a bit, so pay close attention to this. So here's what we're going to do. We're going to say let u equal to tangent inverse of x. Okay, so now what happens is, if you take a look at this, I'm going to come back up here, and what's going to happen is this is going to turn into cosine of u. Okay, so that becomes u because simply that I use substitution. So now look at what happens here. What's nice is we're saying, look, If you could tell me what cosine of u is, that's the same thing as telling me what cosine of tangent inverse of x is. So it's kind of like, it looks much simpler. So my goal now is to find cosine of u. How am I going to do that? Well, if I come back down here, since u equals to tangent inverse of x, by definition, that's the same thing as tangent of u equals to x. And I'm going to put this as x over 1. Okay? And so let's simplify this out. Now, look, one thing I want to point out is, and since I use the definition of tangent inverse, this u has restrictions of what? What were the restrictions of tangent inverse? It went from 0 to pi over 2. So u is from 0 to pi over 2. And you'll see where this restriction will come into play. But 0 to pi over 2 means what? I'm either in quadrant 1 or, never mind, tangent inverse has restrictions from negative pi over 2 to pi over 2, which means I'm either in quadrant 4 or quadrant 1. Okay? So, coming back to this. In analysis, when we learn trig, we learned that tangent by definition is y over x. Okay? So now look, by definition, since tangent is y over x, one thing I want to point out, and I kind of don't like this, maybe I shouldn't have picked x here. When we say y over x, the x in the definition of tangent isn't the same thing as this x. So I'm going to call that like a script x. So here's what we know. By definition, tangent is script y, which by what is y over here? If it's y over x, y here is just x over, and I'm going to put script x because this x isn't the same thing as that x. That's just 1. Okay, so remember, I'm just basically saying this. Tangent of theta by definition is what? Y over x. So if you look at this, y is x. This script x is 1. Okay? Now, to find cosine of u by definition, cosine of u is what? It's script x over r. So look, I have x, which is 1. I just need to find r. Now, I'm sure you guys remember how we found r. We find r by using the Pythagorean theorem. So if script y is x, script x is 1, then r would be what? Square root of x squared plus 1. Okay? And once you do that, then you could come up here and answer this question. So cosine of u is what? X over r. So it'll be 1 over the square root of x squared plus 1. Okay? Oh, and one other thing I forgot to mention. When you use the Pythagorean theorem to find r, oh, actually, never mind. R is always positive, so we have nothing to worry about. These restrictions help us decide if, for example, if I didn't know I had to take if x could be positive or negative, this restrictions would make it obvious to me that x is a positive number. Okay, but for this case, since r is always positive, I don't care about the plus or minus because r is always going to be positive. So that's not concerning me. So then there you have it. We just simplified cosine of tangent inverse of x, which my answer is 1 over square root of x squared plus 1. Notice how my solution is in terms of x, which that's exactly what I wanted. If my solution wasn't in terms of x, then there's something going on there that's incorrect. Okay, so that is my solution, and notice how I used substitution. I just went back and forth until I got to my solution. Okay, so you'll definitely have more homework question based off of this stuff, so you'll get some practice, and if there's anything that you need clarification on this example, feel free to talk to me and I'll be more than happy to clarify it. Okay, so that pretty much takes care of this chapter, and so our review of analysis is pretty much done. So get ready to do some exciting calculus after chapter 1. Okay, so I'll see you in class. Take care.